In the last video, in fact, in the last part, we discussed about some properties of matrices and vector spaces. For example, basis, rank, dimension, etc. Now, that is all talking about the properties of a particular vector space. Now, in this particular part, we are going to study the relationship between two vector spaces. So, whenever we talk about relationships, we need a pair, and we have a pair of vector spaces. So, maybe one v, another w, and we want to find out whether there is the relationship, how is that relationship goes into. So, whenever we talk about relationships, the one of the special relationship is function. Function's other name is mapping, and in this particular video, in this particular part, we are actually going to focus on that. We are also we actually we are going to focus more on linear mapping rather than on all the mappings. So when we say it's a mapping, it is a function, and it has already two properties, that the whole domain is mapped, first thing, and the second thing is every element in the domain has exactly one image in the codomain. So which means that you do not have um, two images. You cannot have two images in the codomain, and you cannot have zero images in the codomain. So that is the primary importance in case of functions. But now we are going to study about linear functions, so linear mappings from one vector space to another vector space. Now when we are saying that it is from one vector space, it means that the values taken by that function is a number of values. So the complete vector goes into the function, and a vector is spits out. So from one vector to one vector space to another vector space. So another vector space means it has the output is also a vector. Now if output is also a vector, it means it is consisting of a number of outputs, which essentially means that you have a function that returns a number of values. So let us go ahead and try to see what mathematically we can say about it. So when we say that a mapping is linear, it means that it preserves the structure of a vector space, because vector space are already linear. So we always talk about linear combinations. We always say that, okay, whenever the vectors in a particular set fills up their linear combination fills up a space, then it makes a vector space. So vector spaces are themselves linears, and we are now going to find out the relationship between two vector spaces. Now when we are going to do that, we want that the structure of linearity is still holds. When so what does it mean by structure of linearity? So let us try to understand it more formally, and by these two equations. So it says that these two things should hold to maintain the linearity, which essentially what it means, it means that the vector addition, the product of vector addition, when it is mapped to the same point, which from which if the individual vectors are mapped to, and then vector added, right? Similarly, if a scaled version of vector is mapped, then it is equals to the first mapping and then scaling. So which is equivalently actually which is equivalent to say this one as well. So if you say this or this, it's same. The both are equivalent actually. Now we know that we can see we will in fact we will see that any matrix can represent any linear transformation or any linear mapping. So when we say that, it means that any matrix actually behaves as a linear mapping, and every linear mapping can be converted into a matrix multiplication. So as of now, I'm showing you one part that matrix can or matrix shows linear mappings. So let us see that. So if we assume that A is a matrix and it is a linear mapping corresponding to phi vector, then we just look at these two properties, and these two properties seems to be very obvious for matrices. Matrix multiplication, because matrix multiplication is distributive over vector addition, and the scalar multiplication can be done later on after multiplying the matrix or before multiplying the matrix, so it's same. So since we can do it anyways, that's why we say that matrix can be termed as or can be taken as linear mapping. So all the matrix multiplication, all the matrices can represent one or other linear mapping. Now let us consider or let us cover some examples to understand it more and try to find out their matrix equivalent. So let us say, see the scaling is an operation which scales a particular vector by a certain amount. The amount is fixed for a particular mapping, for a particular linear mapping, this amount is fixed. So if you want to scale a particular vector, it will scale or it will multiplies its length, or its length is multiplied by some constant value. Let us try to see whether it what it is. So for example, we take a mapping that actually uh, changes a vector into twice of its value, right? So we see that it follows both the properties, and that's why scaling is a linear mapping. Now let us see another example about rotation. Okay, so when I want to rotate a particular vector by a certain angle, so you can see in this particular thing, so let us suppose that the original vector u is shown from the black arrow, which is at angle alpha from x-axis. Now we want to rotate it by a theta angle and let it reach to the uh, beta from x-axis. So the coordinates of the new point v, let them be x and y n, can be found out using these equations. And essentially what you find is that the phi of xy, so if phi is representing the rotation, then phi of xy is actually representing this mapping. So if you see this, then let us try to consider this way, that you will come up with the fact that this is also follows all the properties of linear mapping. So this one, and again if you try it with the second scaling condition, you will find that that also follows, and hence this also falls under linear mapping. Here it is proved, actually here it is proved. Let's go ahead and then see for more. So we say that we also think that differentiation can be represented as a linear mapping. So let us suppose that there is a function defined on functions. So phi is a function, that is defined on functions, such that phi of f of x is equals to derivative of f of x. Now to know whether it is a linear mapping or not, let's try to find out whether those two properties are still fulfilled or not. So you see that with this particular with this particular thing, we are able to see that yes, it is a linear mapping. And again, we can see the second condition also holds. So we see that there are a number of operations, number of things that can be represented by linear mapping. And since we have seen that we can work with matrices, we can, and if it is possible that all linear mappings can be converted into matrices, these all can be automated and can be done through program. Let's try to see another example which is a simpler one and checks out a more concrete thing. For example, let us assume that this is your example where f of x, y, z. So it takes a vector of 3 dimension and it spits out the vector of 3 dimensions. So it looks like this one. So if it is so, then is it a linear mapping or not? So let us see it. We'll prove both the things and we find that it is a linear mapping. So if you check out this one, this particular proof, the first property is proved, and this is where the second property is also proved. Okay, so a lot of things can be represented as linear mappings, and they may be fruitful for us to understand them. So let us go ahead about identifying the mappings in a more concrete way. There are certain types of mappings, and we have already heard of them also, like 1-1 mapping and onto mapping, or 1-1 onto mapping. So these are three mappings that are most interesting mappings, and generally we talk about them because one of them is allowing us to undone a particular mapping. Undone means if you have done a mapping, if you have taken such a step, can you go back? So for example, if you have a function that maps to a value, and then looking at that particular value, can you identify which was the input? What was the input that has taken you to at this particular place? So such mappings are called bijective mappings, which are 1-1 and onto mappings. So there are these are some definitions. So I may be you may read it. So isomorphic mapping is linear and bijective. Endomorphism is within the same vector space, and automorphism is again within the same vector space, but it is linear as well as bijective. So basically, it is actually um, moving to itself, and it has to be invertible or undoable mapping. So let us go with some more examples and um, try to see what does it mean by uh, a bijective mapping, or a mapping whether it is a bijective or not. So let us try to understand that, and then we will see in the next part whether how you can represent a particular linear mapping into a matrix form. So consider x square, graph of x square. So this is x square graph, and this is another graph which is y square is equals to x. So if you want that x square y is equals to x square is a function, and its inverse to be a function, both of them to be a function, because once you say that it should be bijective, then it means that f of x and f inverse of x, both of them should be a function. Now, looking at a function through graphs, it is easier to identify whether they are bijective or not. So let us see how. So if you see the definition of function, the function says that it should have exactly one value at any place. So it has, if you take x, a particular value of x, it for a particular value of x, there should be exactly one value of y associated with this. Which means that if you take a vertical line, it should cut the graph exactly once in the whole domain. Which essentially you can see that if you take a vertical line, and it will cut exactly once only, so it won't cut at two places. So you take any vertical line and it will cut exactly at one place, and hence it's a function. Now let us going to the second, which is actually depicting its inverse. Now you can see that if you draw a vertical line, it cuts at two places, and that's why it's not a function. In fact, if you draw a negative quadrant, negative y, there is nothing is there which is cutting. So the graph is not there for negative values of the domain, right? So if it is not there, then also it is not a function. So what we need to do, we need to omit this part from domain of inverse. And again, the problem lies with here, because this portion is cutting twice the graph. So we have to remove either this part or maybe this part. Okay, or maybe this part we have to remove. So some one of the parts should be removed so as to make it a function, else it won't be a function. So that's how we say that possibly you can say that this forms a function. If you are talking about a y is equals to x square, this forms a bijective function, which is invertible function. Thank you for now for this video.